Hi, so in this video we're going to finish chapter 4. So this section is 4.2 of our least squares regression. So in section 4.1, we looked at scatter plots, looked at the idea of linear and nonlinear trends. If it's linear, we looked at positively and negatively associated. We looked at something called the correlation coefficient and this R value and how it measures kind of like the strength of the model. Things of that sort. So now what we're going to look at is more about how to build the model and interpret the least squares regression model. Right. So before we jump into some of the content, we kind of have like this warm-up example. So we're given this generic data set. It's not really in context, just we have some x and y values. And we're asked to find a linear equation that relates x, the explanatory variable, and y, the response variable, by selecting 2 points and finding the equation of a line containing the points. So we're given these 2 points. Right, so the first thing that you're going to want to find is the slope. Right, so when you're given 2 points and trying to find an equation of a line, you'll want to find the slope, which is y2 minus y1 over x2 minus x1. So I'll let this be 0.1 and this guy be 0.2. So y2 would be 1.9 minus y1, which would be 5.7. And then x2 would be 6 minus x1, which is 2. So if we subtract those, you should get negative 3.8 in the numerator and 4 in the denominator. So when you take negative 3.8 divided by 4, you get negative 0.95. Right? So generally when we find an equation of a line with 2 points, oftentimes we want to put it in slope-intercept form. Where we have y equals mx plus b. Right, so then the 2 numbers we want to have an equation is we want to know what m is and what b is, right? Where m is the slope and b is the y-coordinate of the y-intercept, right? So to be able to find b, we can just plug in one of the points and the slope into that equation and solve for b, right? So I'm going to plug in the first point to 5.7 and the slope of negative 0.95 into the equation and solve for b. So we would have 5.7 equals negative 0.95 times 2 plus b. So that gives me 5.7 equals, so negative 0.95 times 2 is negative 1.9 plus b. So then I can add 1.9 to both sides. And I'm left with 7.6 equals b. Right? So now that I know slope, I know my y-intercept, now I have equation of a line, right? So the equation is going to be y equals negative 0.95 x plus 7.6. Right. So then we're asked to graph the equation on the scatter plot. So I can just make a mark on my points. So we were using the points 2, 5.7 and 6, 1.9. Right, so there's only one point here that has an x value of 2 in our data set. And then we have 2 values that have an x value of 6. I want this one, the 1.9, so I'm going to be looking for the one that's shorter, right, not as high. So that would be this point. So then to graph my line, I would just have a line connecting those 2 points, right? So I'm going to try so I'm just going to insert a line. Right, so you could draw this by hand using a straight edge. And you should get something that looks like that, roughly, right? So there's that equation plotted on the scatter diagram with our data points. So then below it, it says to use the equation to predict y if x equals 3, right? So my equation, I'm just going to plug in 3 in for x. So we would have y equals negative 0.95 times 3 plus 7.6, which equals 4.75, right? If you plug that in your calculator, right? So if we go on the next page, we're going to talk about what's called a residual. So the difference between the observed value of y and the predicted value of y is called the error, or specifically we call it the residual, right? So something that's important to think about is understanding this observed and predicted value, right? So just to make a note, the observed y, this comes from the data, right? So this is actually observed, right? Something that we saw in the data. And then we use just y to denote the observed y, right? Where the predicted y, this comes from the model, right? In other words, it's you use the equation, right? The linear equation to find, and so that way we can tell the difference between the two. We're going to use the symbol y with a caret key above it, and this is read as y hat, right? So we use y hat to denote the predicted y value, right? So if I look at this table here, or this graph here, the scatter diagram, this red dot, this came from the model, right? So this is from the model. This was the question we just did on the bottom of the last page, right? We plugged in 3 into my equation and got an output, a y value of 4.75, right? So that 4.75 value, that's my y hat, right? That's the predicted y value for x equals 3, where this data point here, right, this data point, and it's labeled there, that is an observed value, right? Because that's a data point. That's something we actually observed and measured and collected. So we call that the observed. So my y value is going to equal 5.2, right? So you can see here, to calculate the residual, you're going to take the observed y minus the predicted y, so 5.2 minus 4.75, and we get a residual of 0.45, right? So that's the error that we're finding for x equals 3, right? So how we can write that, so for residual we usually use an e, let e be the residual. So an equation for calculating the residual is e equals y minus y hat. Right, so that's just an equation to calculate the residual. So the idea of what we're going to be doing, we're going to try to reduce this residual, right? Because this residual is an error. It's the distance in between our model and the actual data points. So we want to minimize that as much as possible, right? So that line that we had chosen on the last page, the line seems to kind of model our data, but it's not like the best line of fit, right, or the least squares regression line. So the least squares regression line is going to be the line that minimizes the sum of the squared errors, right, or residuals. So what we would have to do is calculate the residuals for each of the data values, and then square that, and then add those up, and that gives me a sum. And I want to try to minimize that number as much as possible. And the very last thing we're going to do is look at how to actually calculate that sum of squared errors, right? So this activity, next activity, so you can read over what's in this box if you'd like, but I went over all that stuff already. So this next activity is using StatCrunch, and it gives us a little bit of a hand-on application with minimizing this squared residuals, right, the sum of the squares. Right, so I have StatCrunch opened up, and it tells us what to do. It says go to StatCrunch and select applets, and then go to regression, and then by I, and then it says hit compute, and then so it randomly has some points in here. It tells us to hit reset, and then to add 8 points that has a positive association with it. Right, so I'm just going to add some points in, and something you'll notice with how this program works, it says just to enter the x value comma the y value excuse me, without using parentheses, and that's how this works, right? So I'm going to enter the point 1 comma 1, right? I'm just going to make up some points, 2 comma 3, add point 2 comma 3.5, 2.6 comma 4, 5 comma 7, or I guess I typed 4 comma 7, add point 5 comma 8. So we need 2 more. How about 10, 10? And let's do 11 comma 15. Okay, right. So I have some, dots here that have this positive trend to it. And if I hit this, check this box, that's actually showing me what the regression line is. Right, so that's the line of best fit to fit this data. That's the line that minimizes the sum of the squared errors. Right, but if I uncheck that, what we have is this green line where I can move these endpoints around, and you can play around with this. And you're trying to reduce down this number, this SSE. That's the sum squared of the errors, right? That's the sum of the square of the residuals, in other words. We want that number to be as small as possible. So what's in green is telling me what this green line is, right? It tells me my intercept of that line currently, the slope, and then the sum of the squared errors. And then what's in the red, this tells me my intercept and slope of the true regression line with the SSE, the sum of the squared errors for the regression line. So when you're playing around with this, it's impossible to get a number less than this, right? Because that's the model, that's the best. And when you move these around, trying to get that number to be as small as possible, right? So that's pretty good, right? So it's pretty close to the actual sum of the square residuals. So if I hit if I check this box now, you'll notice it's pretty much laying on top of one another, right? So the only way to really reduce that down any further is to be on the line exactly, right? Which a little hard to line up exactly, but that's pretty darn close, right? So this is just something you can play around with to see that there's only going to be one line that minimizes that, and any other line is going to be have a larger sum of squared errors, right? A larger SSE. Right? All right, so now what we have is we're given the equation of the least squares regression line, and we're given not necessarily new variables, but maybe some different notation, right? So let's work through this. So let me actually go off to the side and write some things down. All right, so the very first thing that we have is, the least squares regression line is given by y. Let me use this blue. Is given by y hat equals b sub 1 x plus b sub 0, right? Or this could be given as y hat equals b sub 0 plus b1 x, right? It's important to denote that the b1 and b0, that's your slope and y-intercept, right? So the value that's being multiplied by x, that's going to be the slope, right? So in this case, it's going to be the coefficient of x, and over here, b1 is also going to be the slope, right? It's just in a different order, those two terms. So b sub 0 is going to be the y-coordinate of the y-intercept, right? So this is like your m from before, and this is like your b from before, right? Like in algebra class, right? So I have some other notes about y hat, right? So remember that y hat is equal to the predicted value of y, right? So we use it to denote something different, right? So it's important that you have that symbol so we know what we're talking about, right? So another thing that I want to mention is that y hat is an estimate of the mean of the response variable. So remember, that's the y, right? Response variable is the y for a particular value of the explanatory variable. Which is x, right? So in other words, if you think back to what we wrote on the first page, right? So in part A, we found a model to be, or wait, no, that wasn't the regression line, right? Never mind. Scratch that thought, right? All right. So that's what I want to say there. So then the next thing that I want to talk about are these equations for b sub 1 and b sub 0. So b sub 1, the equation, is equal to r, which that's the correlation coefficient, right? That's the correlation coefficient, which we looked at last section. We have r times s sub y over s sub x, right? So S sub y, that's just the sample standard deviation of the y variables, right? Where here S sub x is just how we denote the sample standard deviation of the x's. Right, so we're using that to denote which variable we're talking about, right? Because now we have two variables. And then another equation we have is b sub 0 equals y bar minus b1 x bar. Right, so this b1 is just the b1 from up here that we calculated. You know, we already know what x bar is, right? We use that for the sample mean, right? So this would just be the sample mean of the x's, and y bar would just be the sample mean of the y's, right? So not too bad, too complicated. Right? So something else to think about, and something I want you to think about with you know, looking at the slope b sub 1 and the r value, right, is that these two numbers are always going to be positive, the standard deviation of y and the standard deviation of x, right? So if I take a positive number divided by a positive number, that tells me this whole thing is going to be positive, right? So it's not going to influence the sign of b sub 1, right? Because this thing is positive. So what's going to influence it is going to be the sign of r, right? If r is negative, I would have a negative number times a positive number, which is a negative number, right? So this would be the r value, and this would be the sign of b sub 1, right? If r is positive, then I would have a positive times a positive, which is positive, right? So this would be the sign of r, and this would be the sign of b sub 1. So notice that whatever r is matches what b sub 1 is, the sign. Right? So that's just a note that we want, is that the sign of r is going to drive the sign of b sub 1. Right? So looking at that equation by hand helps you see that. Right? And if you're not sure, you know, why the standard deviations of y and x would be positive, if you look at the equations, right? So we know that the standard deviation of x, the sample standard deviation of x, is equal to the square root of the sum of the x's minus the means of the x's squared all over n minus 1, right? So I'm taking the square root of a value, so I know that's going to be greater than or equal to 0. Right, but in this case, you know, all practical purposes, this is just going to be greater than 0. It's not going to really ever be 0. So then S sub y's would be the same equation, right, except the difference is we would be taking the y values minus the x bars squared divided by n minus 1, right? And that should be y bar, right? Y minus the y bars. Right, and if you wanted, you could use the subscript I, right, just to note that those are different different values, right? But this is also going to be bigger than 0, so that's why the s of x and s of y is going to be bigger than 0, right? In other words, it's going to be positive. Right. So we looked at everything in this box, just try to look at it separate, so I try to break it up in smaller chunks to make sense of it. And then the next example we have, we want to use the drilling data. So this is the same same data that we looked at before, right? It's on canvas drilling.csv. And you can find that. So the first thing we want to do, part A, is we want to find the least squares regression line. So I actually want to show you how to do this using the equations. So I have this already pulled up in StatCrunch, right? And I mean, if you think about what we're going to need here, right, by looking at the equations, we're going to need to know r, the standard deviations of each variable, and the means of each variable, right, in order to calculate this. Right, so coming off to the side, things that we need to know the r value, we need to know s of x, s of y, and we need to know x bar and y bar. Right, and just as a friendly reminder, the x variable is depth and the y variable is time, right, that we used before. So instead of doing everything by hand, I just want to get comfortable with those equations. I'm going to have R calculate, StatCrunch calculates these things for me, right? So if I go to Stat, Summary Stats, and then Correlation, and select my two variables and hit Compute, that's going to give me the correlation coefficient, right? So that's my R value. So I could write that down for that. So then to find the other values, I would go to Stat, Summary Stats, and then Columns. I'm going to pick both variables again, and then I want to know the mean and the standard deviations, right, and hit Compute. And then I have all of those, right? So the depth is my x variable. So 126.25 would be x bar, and s of x would be the standard deviation, right? So then this value, this 6.985 number, that would be y bar, right, the mean of the y variable. And then this variable, or this value here, 0.78, that would be s of y, right? So we found all of those. So let me just write this down, right? So R was 0.77282153. S of X was the 52.228736. And I'm writing all of 8736. Writing all of the digits that StatCrunch gave me. So S of Y was 0.78077. Was that a 4 or a 9? Let's see. S of Y 78077,419. And then X bar was 126.25, and Y bar was 6.9858 and 3 threes. Right, so now that I have, though, I can calculate these values, right? So the slope, right, is b sub 1. That's equal to r times s sub y over s sub x. So just filling these values in, we would have the following product to calculate. Right. So if we throw that in your calculator, you should get 0.011553099. So then b sub 0 would be equal to y bar minus b sub 1 times x bar. So plugging those values in, we would have 6.9858333 minus 0.011553099 times 126.25, and that gets me to be 5.5272658. Right, so if you remember right, my model is y hat equals b sub 1 times x plus b sub 0. Or in this case, right, instead of writing y and x, typically what we'll do is we'll write a variable that helps me remember the context, right? So in other words, we would have time hat equals, so b1, I'm going to plug in the value. I'm going to round to 3 decimal spots, so that would be 0.012, and then times the depth plus b sub 0, so I'll round at 3 decimal spots. So that would be 5.527. Right, so that is my least squares regression line. Right. So I want to show you how you can find this on StatCrunch also really quick. Right, so if I go back to my StatCrunch with my data, my drilling data in it, I can go to stat and then regression and then simple linear, click that, and then we're going to select what the x and y variables are, and then I can hit compute, and this gives you a lot of information in it. So I'll just take a screenshot of this. I want to write on it. And then also I want to point out another thing. Notice it says 1 of 2 at the top. If I click on the right arrow here, this just gives me a nice scatter diagram, and the red line is that fitted line. In other words, that's the least squares regression line of best fit, right? So that's that line that we found using this model. So this is the printout for it that StatCrunch gives you, and I'll just warn you that it gives you a lot of values that we don't necessarily need. So I'm going to highlight what you want to pay attention to, right? So the dependent variable can be helpful to you, right? That reminds you what the what the y variable is. So then the independent variable is also important to you, right? That reminds you what the x variable was. This next line, this is the fitted line equation, right? The model. So this is the model. This tells you your sample size, right? So that tells me I have 12 rows of data. And then the R, the correlation coefficient, is something else that you should know, right, and be aware of, right? That's just your R value. Excuse me. So this R squared, we're not going to worry about in this class. The estimate of error, we're not going to worry about in this class. This column, we won't worry about. Actually, all of these numbers we won't worry about. And then this number we'll deal with, the sum of the squares of the error, and this number, right? So the intercept is just your b sub 0, right? And the slope is your b sub 1, right? So those are your estimates. And then all of these we don't need. right? So that value is your sum of the square of the errors, right? That's what we're trying to minimize. Right, so that's how we read this, right? And again, all those things I crossed out in red, you don't need to worry about, right? I know it seems overwhelming, but that's how the printout is, and excuse me, all that stuff I crossed out is really useful and important, just beyond the scope of this class, right? So you can see here that the values that we calculated by hand are lining up with the values found by using R or StatCrunch, right? We could find it using R as well, but we use StatCrunch. All right, so part A is what we did, right? Was finding the equation of the regression line, which we did. So that was time hat equals 0.012 times the depth plus 5.527. So then part B is to predict the drilling time if the drilling starts at 130 feet. So what we want to do is use this equation and plug in depth equals 130 feet and find the appropriate time hat value, right, that my function gives. So we would have time hat equals 0.012 times 130 plus 5.527, and this gives me 7.087 minutes back, right? So then what we're asked to do is the observed drilling time at 130 above or below average, right? So the observed drilling time is from the data, right? So if I go back to StatCrunch, right, here's the table of my data. I'm focusing in on this row 6, right? So for 130 depth, this is the observed time, which is 6.93, right? So the observed time, right, the y value was 6.93. The average value, right, that's going to be the y hat value. That we found that in part B to be 7.087. So we're thinking about, is my observed time above or below average, right? So the average value is bigger, so we're below average, right? So the observed value was below average for 130 feet, right? So this value here, 7.087 minutes, that's going to be what we would expect the average to be for, if we looked at, a lot of times that were 130 feet above the drilling, right? That's what we would expect the average to be roughly, right? That's predicting. So then part D is to draw the least squares regression line on the scatter diagram of the data, right? So rather than drawing that by hand, remember we had that in StatCrunch, right? So if I hit this right arrow, that's the picture we're after, right? So if you wanted, you could go to Options, Copy, and just copy that image, and there you have a nice graph for part D in your notes. All right, so now what we want to do is look at interpreting the slope and the y-intercept of the least squares regression line. So with the drilling data, the equation that we get, and here we rounded the 4 decimal places. We get y hat equals 0.0116x plus 5.5273. So what we're asked to do is interpret the slope of the regression line. So the slope, right, is going to be this value, 0.0116. So, in algebra class, you should know that slope is the change in y over the change in x, right? You take y2 minus y1 over x2 minus x1. So, if I have a slope of 0.0116, that can be written as 0.0116 over 1, which tells me every time x changes by 1, my y value is going to increase by this 0.0116 number, right? So this is my change in x here, this is my change in y. And if we put this in context, the change in x was the change in depth, and the change in y was the change in the time. Right, so you can see it is written out here that, for each additional foot of depth we start drilling, the time to drill 5 feet increases by 0.0116 minutes on average. Right, and that on average part's important because it's not going to be exact, right? If we were, in algebra class and that was a slope, then that would exactly happen. But that would, roughly happen in stats, right? Because not all the points are going to lie exactly on the line, right? So that's why we say that on average part. So then if you want to interpret the y-intercept, right, the y-intercept is going to happen when your x value is 0, right? So the y-intercept of this regression line was that 5.5273. So to interpret a y-intercept, we need to ask two questions. One, is 0 a reasonable value for the explanatory variable, right? So in this case, the explanatory variable is depth. So would it make sense for to have a depth of 0? And then also, we want to think about, do we have any observation values near 0 that exist in the data set, right? So a value of 0 is reasonable because, for the drilling data, because that would just indicate that you would begin at the surface of the earth, right? Because if your depth value is 100, that just means you're 100 feet down, right? And then also the smallest observation of the data is x equals 35 feet, which seems reasonably close to 0. So the interpretation of the y-intercept seems reasonable here, right? So the time to drill 5 feet when we begin drilling at the surface of Earth is 5.5273 minutes. So that this sentence is a interpretation of that y-intercept. And notice how we put it in context, right? So we tried to make it as clear and as meaningful as we can, right? So that in context part is important. Right. So then we have a caution here. So if the least squares regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, we say the researcher is working outside of the scope of the model. So you should never use a least squares regression line to make predictions outside the scope of the model, because we can't be sure the linear relation continues to exist, right? So typically what we think about there is the interpolation versus extrapolation. So these are two terms that we typically talk about here. So interpolation is where you're making predictions inside your data, and extrapolation is where you're making predictions outside of your data. Right, and here when I'm using the term data, I'm thinking, specifically about the x values, right? That's what we focus on. So what I want to do now is I'm going to grab the scatter diagram from this drilling example and draw on here and show you where the interpolation and extrapolation would be. Right, so you know this value here, this x value that goes with this data point, this would be the smallest x value, which is 35. And then this dot here is my furthest dot to the right. Right, so that would correspond with my x value of, let's see, what was that one? Right, so if you look at the data, the biggest depth is 190. Right, so this would be 190. So if you're inside of 35 to 190, then that's referred to as interpolation. So that's good. Right? If you're outside, so in other words, if you're using the model to predict something like an x value bigger than 190 or smaller than 35, then if you're going on these outsides, that's referred to as extrapolation. So that's bad. Right? And I'm using those terms kind of loosely, you know, good and bad. But the idea is, if you know, look at this sheet, this gives you some background information on extrapolation. So I took this from another textbook, but what I want to focus in on is this part here, this for example, over extrapolation, right? And I'll show you why extrapolation can be dangerous. And the whole idea is your data may look linear for what you have, but it may not continue on, you know, to be linear. So like here, we looked at data for the median age at first marriage for men and women, and looked at time, and we came up with this model, this equation for the years 1890 to 1940, right? So this looks like a good model. So then these blue dots here, this represents our data from 1890 to 2010, right? So that's you can see it in this graph as well, just that narrow part, right? So we have this graph, this data with just 1890 to, no, that was 1910 or 1940, right? Sorry, that part is just to 1940, right? So that graph looks to be very linear, right? It makes sense for that to be a linear model, and that's what we have highlighted in blue, right? But it turns out that as time went on, we have these other possibilities, right? So these green dots and these red dots. So notice what happens is the blue dots don't continue on forever. We have like this turn happening on the green dots, and then it looks like maybe like almost like a linear function again, but now it's increasing. It's like switched directions, right? So my line of best fit, right, would have looked something like this, but that didn't continue on, right, past our known data. So when we're making estimates outside, that's why it's dangerous, because we don't know if my data continues to be linear. All right, so then the last thing we want to do is compute the sum of squared residuals. So remember, the least squares regression line is the line that minimizes the sum of squared residuals. This means that the sum of the squared residuals is smaller for the least squares line than for any other line that may describe the relation between the data values, right? We looked at that at the beginning. So here's an example where we're using our least squares regression line from the drilling data, and here's a table computing the sum of the residuals squared, right? So you can see here, this column represents the x values, this column is the y values, this column is my y hat, right? My predicted values and my observed values was y, and then here are my residuals, you know, e equals y minus y hat. So to get this number, we're finding the difference between these two things, right? So taking this number minus this number, we get negative 0.0533. And then this number is just these numbers squared, right? E squared. And then so we're going to sum all these up, this column up, and we get the sum of the residual squared, right? So that's how you find that value. And so any other line other than the least squares regression line will have a sum of squared residuals that is greater than 2.70119, right? All right. So I want to practice quickly going through calculating the sum of the squares of the squares of the residuals. Using the XY data that we had, right? So if I try to make a table, right? So here's my X, here's my Y values, and then here would be my Y hat equals, we had 6.55 minus 0.7136 times X is that equation. And then the error would be E equals Y minus Y hat. And then here we're just going to take E squared. All right, so just filling that in, we had 0, 5.8, and then 2, 5.7, and then 3, 5.2, and then 5, 2.8, and then 6, 1.9, and then 6, 2.2. Right, so then to calculate the y hat value, we're just going to plug in the given x value into this function, right, this equation. So we would have y hat equals 6.55 minus 0.7136 times the x value, which is 0. So if we throw that in your calculator, you get 6.55, right? So then for this next box here, I'm going to plug in 2 into this equation, and for x, and to save time, you would get 5.1228, right? So then if I plug in 3 into that function, you get 4.4092, and then if you plug in 5, you get 2.982, and then the last two have the same x value, so if I plug in 6, you'll get 2.2684 for both of these. Right? So then now to calculate the error, the residual, you're going to take y minus y hat, right? So you're going to take this column minus this column. So for the first one, you would take 5.8 minus 6.55, and that gives you negative 0.75, right? So then for this next box, you would take 5.7 minus this number, so you get 0.5772. The next one would be 0.7908, and then negative 0.182, and then negative 0.3684, and then negative 0.0684. Right? And then now for the last column, we're just going to take these values here and square them. So to find the e squared, right, for the first one, you would take negative 0.75 quantity squared, which gives you 0.5625. Right, so then take this number squared, you get 0.33316, and then take this number squared, you get 0.62536. Then take this number squared, you get 0.033124. Take this number squared, we get 0.13572, and then take this number squared, we get 0.004676. Right, so then if I add these up and find the sum, right, that number we get is 1.694543. So that is the sum of the square root of the errors, right? So we abbreviate that as SSE typically, right? You could also show it as the sum of the errors squared, right? E sub I squared. So that's equal to the SSE, which is equal to 1.694543, right? So if I go into StatCrunch and pull this data over, if I go to stat, regression, simple linear, and pick x is my x and y is my y and hit compute. So if you remember when we looked at this table last time, I told you this SS and the error, I would show you at the end of how to find that, right? So this number is what we just calculated in the table, right? So you can see how that lines up, right? And that might be, a little off, just like with sample standard deviation, because of some rounding and things, but you can see we got pretty much that value. All right, so that's all the material in this section. Make sure you let me know if you have any questions. Thanks.